let's take a look at 15.4, double integrals in polar. So I went ahead, I think I did the previous couple times, wrote up some of the theory. So maybe at this point you can pause it and write some of this up, but I'll explain it as I go. And then we'll focus on the problems more as I work stuff out. So first recall polar coordinates. So polar coordinates, you have a polar axis like this. And then to describe a point in space, it's the distance from the origin. So this would be like 0, 0. As you would in rectangular, right? Distance from the origin to the point. So that's your value r. And then you sweep out an angle, theta, from the polar axis like this. So a point over here, you'd sweep all the way around like that. And so you indicate that as the distance r and then theta. So it's r theta. Then to describe or interchange between your y and your x, we use, of course, all of this. So you use that transformation between polar and rectangular. So I'm sure you've seen that before. R cosine theta. So x is r cosine theta. Right, here's x is adjacent over hypotenuse. And then y is r sine theta, which is opposite over hypotenuse. And then you have Pythagorean identity as well. Theorem, basically, actually. X squared plus y squared is r squared. So we're going to use that concept in our discussion here. So what we do is we take two functions. So basically start writing this down if you haven't already. Do a polar axis, and then you have a lower function like this. R is g1 of theta. So r is respect to theta. And then you have another function like this, r with respect to theta r. So you call that g2. Some assumptions. G1 and G2 are continuous, and G1 of theta is less than or equal to G2 of theta for theta between alpha and beta. So here's your alpha, and then here's your beta. So that's all the setup. And then what we do is we will partition. So down here, I started saying it here. We will partition the region. So this whole thing is your region R. So you partition the region R. But what you get are not exactly rectangles. You get what's called a polar rectangle. So let's look at this rectangle down here. I'll leave it like that. So you have R1 and R2. Right, so write that down. And then we have what's called the average radius. The average is basically the sum of these two over 2. So that's the average radius, which would be right about here. So we're going to call that r bar. So the average radius is a half, one half, so the average of R1 and R2, essentially. So then we can describe, and so keep that in mind for now. Then what we can look at, or going to look at, is the area of each one of these polar rectangles. So the area is basically this entire sector minus this sector. So that's what gives you this r sub k, or the area of r sub k. So delta A, so look at 1/2 r squared delta theta. That's the area of this entire thing. So you can look up area of a sector is that. Let me go and write that down. So this is area of a sector. And then you subtract off, or we would subtract off the lower part. So lower part here would be 1/2 r1 squared delta theta. Right, this piece here. So do a little factoring on this over here. And you get, so you basically have to factor out the 1/2 in front, factor out the delta theta in the right side, and then you have a difference of squares. So in this difference of squares, your R bar is right here. It's so this, let me highlight that. So what you get is this is right here, which is the average radius. So we're going to convert that then into just R bar. So remember, when you pick an arbitrary value in the interval, it could be anywhere. It could be this endpoint in here or here. What we're going to do is pick it to be the average radius. So the argument goes in the definition, since it's arbitrary, you can then, and it works, essentially when you do the limit, everything works fine. Then you can pick a particular one if you want. And that's what we're essentially doing here. So this ends up being R, and this will be your dr and your d theta in your formula. So now we're going to partition and do some of the definition stuff. So we partition R. We're going to choose or set the norm to be the largest of the diagonals of the R sub k's. We're going to choose a point in R sub k such that R sub k is the average radius. Then you get delta A is the R delta theta. Then when you take the limit as the norm of the partition approaches 0 over all the sums, and then you have some function possibly of your delta A's, you get your delta A is all of this. So what essentially happens then is you get this extra factor of R here. And because of that, your formula has the R dr d theta. That's what's basically the most critical, is you're integrating over the region, dA. You get lower function, upper function, and then you evaluate from alpha to beta, right, up here. So you're going to go from alpha to beta, right, like that. And then you get your function, and then R dr d theta. You must put this in your formula. So we will convert back and forth between rectangular and polar. So let's do an example of that. So now let's evaluate this function. So this says use polar coordinates to evaluate. So before we do that, just take a look at it. Would you want to do that just in rectangular? And frankly, I'm not sure what we would do. There might be formulas for it. I'm not totally sure offhand if there is a nice one. But with respect to y and it's raised to the 3/2, not real clear right away how we would do that. So let's do this. So here's the important idea. The integrand may be substituted directly. So in other words, you can, for this part here, whatever you know about x squared and y squared and everything else that might be there, you can do a direct substitution. You don't have to do any playing around. What you need to do, though, is you cannot substitute directly for your limits of integration. You have to interpret your limits of integration as functions. Basically, it says y equals 0 to y equals square root of a squared minus x squared. Then it says x equals negative a to x equals a. And you have to interpret that. You have to graph that. So the integrand may be substituted directly. And for the limits, so I just said not for the limits of integration. Okay, so that's critical. What we must do is sketch. Whoa, keeps happening. Sketch the region and convert. So over here, we are going to sketch the region. What we have then is we have y equals 0. We have y equals the square root of a squared minus x squared. We have x equals negative a to x equals a. So that's what we're going to sketch. So remember that this is greater than 0. And to simplify that, so keep that in mind. And then to see what this is, here, we can square both sides and simplify. You may recognize it right away, maybe not. If you square both sides, you get y squared is equal to a squared minus x squared. And then that is equivalent to x squared plus y squared equal to a squared. So we can see that's a circle. But it's only the top half. Because you have greater than 0 for the positive square root. So we can graph that circle over here. And it's just the top half. So you want to graph all these. So let's go here. Now this, I got to be a little careful when I graph this because otherwise it won't make it a circle when I do my little circle here. So what I do is I do a circle and then I erase the bottom. That's only because I can use the software element of this thing to do it. Okay, close enough. And so what I go through, or if you use like a stencil, you can do the whole thing and then erase part of it. So then I go through and erase this bottom part. There we go. So it's just that top half. And you can see that the radius is a, so there's your negative 8a. That's your x. And what you have, so that's your region R. And excuse me about clearing my throat. It just happens when I lecture. I don't know what's going on. Okay, then you have, this is what the rectangular pieces would look like. That's your, you'd have to go from the lower half up to the, the top function. But that's not what we're going to do. What we're going to do is do the polar rectangle like this. So you want to put in that polar rectangle like that. And so that's your radius. That's your R. And then you have your angle theta like that. Let me change that a little bit. Let's put that over here. Okay. So the radius R, what that is 0 to a. So you're going to integrate from 0 to a, and then what is your theta going to be? So your theta is going to be from 0 all the way to pi. So 0 to pi is what's sweeping out around that. So you have your we were just converting this, so we're not changing anything. Now the integran, you can substitute directly for your R. So you can just, so x squared plus y squared is r squared, so you can just substitute that directly in. That's what we'll do. So we have the screen getting messed up apparently. We have the integral, let me change the color on that. So we have the integral from 0 to pi, that's your theta, your inside limit is a equals, or r equals 0 to r equals a, and then it's, oops, I'll do that too soon. Your function is what you're substituting for, so it's r squared raised to the 3/2, then it's r dr d theta is what you end up substituting for. So that's what this ends up equaling. And so you get the double integral from 0 to pi, 0 to a, and then it ends up being r to the 4th dr d theta. And you can evaluate that. That'll just be 1/5 r to the 5th, substitute in a, and then you substitute in pi and you're done. So that's just kind of a one step after that. Real simple integration. So it's 1/5 pi a to the 5th. So you can take something really difficult with an integral like this, put it into polar coordinates, and make a real simple integration. That, of course, only works when you have circles and things that are more easier to determine or write in polar coordinates. All right, let's do another one. Excuse me again. So next example. And as we're going, feel free to stop and work problems out. I'm kind of not really doing that. Remembering to stop. There's a few number of questions I don't work them out, of course, so that I have the answers. All right, let's look at this example. Oops. Fine. So this is an area one. So the integrand will be just 1. So find the area. And you should be writing all this out as we go. Don't wait for my notes. I'll post them later in the week. On the area of the region R that lies outside the circle, R equals A, and inside the circle, R equals 2a sine theta. So this is, what's kind of nice in that you can stop this thing and go look up how to graph that. I won't spend a lot of time recalling stuff because we need to just get through it, but ideally you can go look up how to remember how to graph the polar graphs and things like that. I know it takes time, but we'll do the graph, of course, but you have time to do that. Or you could pause it and do that is what I'm trying to say. So first things first, we need to graph the region. And you'll be able to do this on your calculators if you want, but one's just a circle, and one is a circle that's shifted. So let's do that graph. So we'll do a circle. Well, oops. Let's see how much space I need. Move that down some. So we need a radius A, and we'll do that circle first. So I'll just count 1, 2, 3. I think that's large enough to make it make sense. 1, 2, 3. 1, 2, 3. 1, 2, 3. 1, 2, 3. So I'm going to do a circle there. Going to copy that and then paste it. So redraw the circle. Basically, it looks like that. So it's the top one then is R equals 2a sine theta, And of course, this one is your r equals a. So what we need to do is find the intersection of the graphs. That's one of the critical points to this one. So find the intersection of the graphs. And do you remember how to do all that? Set equal and solve. So you set those two, so you set r equal to r basically. So you say a is equal to 2a sine theta. And then you simplify that. So that's 1/2 is equal to sine theta. So when is sine theta a half and positive? Right, so that's true if theta is equal to pi 6 and 5 pi 6. Okay, so those are special angles. So those angles are here. So this angle goes through there is pi 6. That's your alpha. And then this angle, we'll keep it the same color, I guess, is your 5 pi 6. And then going all the way around like that, that's your beta. So alpha is your pi 6, and your beta is 5 pi 6. So we're going to integrate. Your outside limits will be that theta. It will be from pi 6 to 5 pi 6. And then your representative rectangle will look like this. Let's do purple. So you put one up, so it's like this. I'm not sure how much you can see that actually, but so what we're not actually looking at then is this piece, right? We don't want, let me erase some of that. So this really isn't here, right? We'll leave it like that. So that's your representative polar rectangle that you're adding up basically from this function all the way out to this function. So r goes from a all the way to 2a sine theta. And then you're going to sweep that from here, which is your alpha, pi 6, all the way around to 5 pi 6. So your area change the color on that. Area is going to be equal to the double integral over r of r dr. Well, let's just do it like this first. So let's just say this is just dA. So area is just integrating over r, and then it'll be a 1, right? That's your function, and then dA. That's the general idea for area. There's no height to it. That's like the concept, if you want. And we say, then, let me come down here, give us some room. This is equal to, so we'll go like this. Just so you can see, it comes down here, give us some room. It'll be the double integral as r goes from a to 2a sine theta, and your theta goes from pi 6 to 5 pi 6. And then your integrand convert your dA. So always remember you have to convert your dA So your dA is always your r dr d theta. And yes, we will be able to later change the order of that, but you need this extra little r in there for polar. So it's r dr d theta. And then that is really easily integrable. We'll do a couple steps on it. You can use symmetry on this one. If you wanted to, you could go from pi 6 to pi halves and stop, and then just do twice that. But you have to be careful with symmetry, because if there's a function above it, up here, like f of r theta above the thing, that may not be symmetric. So you got to be to the region. So you got to be careful with symmetry. So don't always just do it if you think so. So let's work this out a little bit, and then you can finish it, or you could maybe start it now to finish it. And pause the video if you want. Okay, so you get the double integral pi 6 to 5 pi 6. And with respect to r, so that's just 1/2 r squared evaluated from a to 2a sine theta, and that'll be a d theta. And you can see now that once you substitute, your r is gone, and then you have just theta. And then your next integration, you'll have integrating with respect to theta again. So then your variable will be eliminated once you substitute in your angles. That's what you want. So this equals, we have a little bit of this all worked out. So that's pi 6 to 5 pi 6, and then I get 1/2 2a sine theta, and then that whole thing's squared minus 1/2 a squared, and then it's of course d theta. So on this one, let's see. You do have to do a little work on this one now that I'm looking at it. So you have the integral pi 6 to 5 pi 6, and then it's 2a squared sine squared theta minus a squared over 2 d theta. I just simplified that a little bit. And so right here, what you want to do, right, let me highlight that. So this right here, because of this, I don't know if you remember how to do that one, but you can use or apply the half angle formula. So apply the half angle formula. All right, so then do that there. Rest is probably just a constant, and then it works nicely out. After that, you get a squared, and then you get pi thirds plus root 3 over 2. I wouldn't say that's nice, but I do have an answer for it. So check that out, see if you can get that. This is a good example. I've put this question on test before. I probably won't be this time, obviously, but this is a good representative example of what we're doing, and the previous one too. Frankly, it's just those types. One is just direct substitution.